Okay, so today's talk, well, the topic is applications of a native distributed graph database in the financial industry. I'm Chen from CreateLink technology. Oops. Okay, first, a very quick introduction of myself. I got my PhD from Waterloo and postdoc McGill, and the first job is in Amex, data scientist, and the second one is Splice Machine, a software architect, working on a distributed relational database on HBase. And then I found my own company in Toronto, Graph Intelligence, working on Graph. And then later, I went back to China and created my own company called CreateLink. And in Chinese, it's 创林科技, okay, in Hangzhou. Well, firstly, a bit of company introduction. Sorry. Sorry. Yes. We founded in 2016 in Hangzhou, China, and we got invested by Baidu in 2018. And then later, Hillhouse, Tencent, and two other famous VCs invested in us. And currently, we are the only graph database startup in China that enters four famous consulting reports globally. And we broke the LDBC SMB record in May 2022. And also we have the, currently, to my knowledge, the largest scale graph up to 5 trillion nodes and vertexes. And our customer include Tencent and 40% of the 5 major banks in China, and also Power Grid. And we're holding a number of patents and a number of recognitions. And then these are the figures that taken about us winning records the recognitions from Tencent because of beating a set of competitors. Well, these are the key clients that we're currently having. Firstly, the major banks in China, like the Agricultural Bank of China, and other major banks like Bank of Communications, Minsheng Bank, Beijing, Shanghai, Guangzhou, etc. And then also major projects from Power Grid and also the Public Security Bureau. Okay, so let's talk about the major theme today. So financial industry use cases. Well, firstly, actually graph application scenarios are everywhere. We can apply on a lot of different scenarios like social network, finance, retail, power grid, telecommunication, government, manufacturer, network, security. And today we're going to talk about financial industry in particular. And of course, we have a set of advantages over relational model. In generally, the first one is that we can do very intuitive modeling. And then people, even with no computation, programming skill, can actually draw their model using our tools to on the screen. And then through a set of drag and click, they can already load data from different relational databases. And then it's very convenient. Secondly, the programming model, we use Cypher. And then it's for the multi-hop query, it's much easier to write, and it's much faster than relational databases. This is common traits of graph database technology, not only particular to GalaxyBase, to our own product, but to all graph databases. And since the major theme today is about banks, and I think one of the special value of graph database in banks is we provide a platform to connect all the data sources from different branches or different services. Data is stored in different systems internally in banks, like personal banking information system, corporate banking information system, transaction system, loan system, securities, and external data sources that the banks might have already purchased. And we, as a graph platform, we actually connect all or a majority of the data sources from different service departments to form a single platform across everything in one bank. And then based on this common platform, we support multiple applications on top. So basically, for the applications, we are using the sociological principles of graph analysis, finding birds of a feather flock. Actually, the principle is birds of a feather flocks together. We find relationship, pathway, community, feature in like identification, credit card fraud application, post-loan fraud monitoring, corporate group identification, anti-money laundering, precision marketing, data governance in all different application scenarios. Oops. Okay. And concerning one of the most important things in banks is financial risk management. The graph way is that we actually build one graph. I just mentioned why the platform-wide graph platform that we built across different departments. And then we use 3 core tags. One is the graph database, and one is the graph computation. And in many cases, a graph platform can provide both, right? The database and the computation platform. And then the third one is the graph analytics tools and graphical user interfaces. And then we provide full cycle real-time coverage concerning anomaly association mining, risk transmission, and community mining. I'll give examples later. So basically, graphs in financial risk management, we have different kind of graphs, like the credit card application graph, transaction graph, corporate conglomerate graph, corporate guarantee graph, enterprise ownership graph, corporate transaction graph, etc., belonging to different service departments. Firstly, I would like to talk about the graphs in the enterprise, corporate banking. The first use case is the excavation of the actual controller. So enterprises and related individuals have intricate holding relationships, and we actually don't know who is the actual controller of everything. And to the right, you can see the blue, the green ones are individuals, and the blue ones are companies. And the very big orange one is the objective corporation. We want to find, okay, the real controller, a person that actually controlling everything. The small orange circle is the actually real controller. And using the graph representation and also the underlying data connections, we can easily find who is actually controlling the entire thing, and then to help the bankers to decide whether or not to issue loans to this company or in some other related companies. It's very straightforward. Another use case in the banking is supply chain risk for corporates. So customer default risk shared by external companies might be transferred to target customers along with guarantees and upstreams and downstream transactions. In addition to their own operating capabilities, banks need to assess the external risk of companies. So here to the right, for example, and every nodes, there are companies, and the blue ones are relatively less risky companies because they're not actually forming a kind of guarantee circle. But the orange ones are more risky because they're one guarantees another and another that comes next. So for example, if one of the companies goes bankrupt, and then correspondingly, whoever that guarantees this company might be severely affected. So bankers will need to know this kind of relationship to decide whether or not to give loans to these companies. And this one, post-loan fund monitoring. Well, the banking industry has launched convenient online financing products that are no mortgage required, convenient and efficient and flexible in use. However, some small and micro enterprises and self-employed individuals do not use the loaned money for the production and operation, but directly or indirectly invested in prohibited fields, such as wealth management, securities, real estate, etc., or lending out money to elsewhere. So how do we actually monitor the money that we've given to companies to see, to make sure that they're being used in the way that they were supposed to? And then using graphs, we can very clearly and in real time, in this case, real time is not that real time, but anyway, to see where the funds are being used. And then if they're not being used correctly, we can directly do some corresponding actions. Okay, now we go to the anti-money laundering. So money laundering process often involves deep chain transfers through multiple core accounts, changing large amount of amounts into small amounts and reducing the risk of being identified. And it's very easy to understand that we have a transaction network, one transfer to another, and then we can easily use graph to represent such a network or reconstruct such a network. within one bank or across banks. And then we can do a lot of actions. For example, we can identify such patterns firstly, and we can block certain transactions, or we can do proper investigation afterwards. And now about personal banking, we have a credit card application risk, right? So in the process of credit card application, personal information and behaviors are easy to be forged. Scoring rules for the individual is easy to be seen through, and hidden fraud groups are easy to cause a lot of losses to banks. And then here, for example, the blue ones are actually people, individuals. And then the orange ones, sometimes are device or a phone number according to the modeling, the graph modeling. And then using graph, we can actually easily see, for example, one credit card, maybe one telephone, one cell phone is used to issue one credit card application, but maybe the same cell phone or one cell phone can, we can see that it has been used to apply for 3 credit cards, and they are closely connected as a group, as a community. And then we can have very explainable results in real time to see or to judge whether or not the new application coming in is more risky than the others. Well, another one is credit card credit limit management. Right, some people cooperate with merchants and use multiple accounts to swipe orders to achieve the purpose of falsifying merchant credit or sales data, or to increase credit card swiping limits. And here, for example, the person to the left, the orange one, owns a set of credit cards and then tries to swipe all of them or many of them in one of the merchants, the green one to the right, multiple times. And then these kind of patterns is only one example of such patterns. And we can use graph algorithm to detect such patterns and then do actions accordingly. And the next one is anti-cashing out. It's like the bad merchants would often use bank cards and acquaintances to complete the loop of cashing out. And the pattern of pure capital flow cannot be seen. And then it's very easy to imagine that to the left is a set of customers, the orange background, and they have a set of credit cards, the blue background, the merchant, a set of green background, and then they have a set of debit cards, the very much lighter color to the right. And they have a associative behavior pattern. And these can be detected and monitored in real time as well. Okay, some success stories. This one, if you're using a Minsheng credit card on the Jiaotong Yinhang credit card, well, it's 2 of the major banks in China, and every credit card application you would go through us because we use graph to detect whether or not it is fraud behavior in the background in real time in less than half a second. So the figure to the bottom right is one example of the one I just mentioned, is that we can see that the bad persons, they're interconnected in their group, and then they're it's like the principle is very simple. It's an economic principle instead of like technical principle to detect this group of people that are doing bad things. Well, this is Shanghai, one of the banks in Shanghai. They're doing very large scale corporate banking risk management. Because they're coupling with the banking ownership relationships and also every kind of like the transaction data based on time and behavior, and can easily accumulate it to trillion scale. And then we are there to support as underlying platform such a large scale computation. Okay, well, the time is limited. Finally, a bit of an introduction of our own platform. Firstly, let me talk about the native graph, non-native, completely non-native, and partial in the middle by storage. So it's very easy to understand, like the one mentioned, Tiger Graph, Neo4j, and us, we're native storage. So from the very application to the end, we're just like the graph. But the complete opposite is non-native, is the application layer you see as graph, but underlying everything is relational. So you have to do translations every time. And in the middle is a majority of the distributed graph databases that we keep the interface to the application, etc., the same as the graph, but we switch the backend from a single machine implementation to a distributed data store, such as HBase or something. We still need to do the translation, because that's a black box to us. We cannot actually control it. We still need to do the translation. That's why although it is distributed, but it's not that efficient. It's not that fast, because whenever we talk about really real-time transactions or operations, we will be slower than the genuinely native graphs to the left. And we are we did everything from scratch, so we're in a genuinely native distributed graph database. To the left is the data sources we have, like relational table or big data framework, and we take data from those different data sources, even if files, and then put into our own storage format, which is native graph format. And we support computation, also built-in computation layer, and the upper interfaces like programming or graphical user interfaces to support upper level applications. Therefore, we control the storage, we can control the computation, and also provide analytics tools so that we can cater to a set of customer pain points. Okay, and one of the major traits of our products, so we provide a number of built-in graph algorithms, and well, that's a lot of many. And then we can also do analytics through the graphical user interface. People can, with no programming skills, they can execute graph algorithms and see the results and guide their actions on screen. Okay, 15 minutes. Thank you. That's everything.
Thank you for the talk. Time for questions. Yuan.
Thank you for the talk. It's very interesting. So I'm wondering, for these credit card fraud detection application, so it has to happen in real time. But if you're having a separate native graph database, I'm assuming all the transaction coming to a operational data store, whether it's a key value store or SQL databases, how do you make sure that the detection of fraud is real time?
Well, one example is in one of the banks. As one application request comes in, we send simultaneously the request to two different backends. One is to us, one is to the relational, the original storage system, etc. And then we do processing in the real time. And for the real time detection, we actually already have a very big graph built based on the historical data. So you can imagine if a group of bad guys, okay, they have applied for, they have submitted 10 applications, and then the 11th application, when they submit the application, and we can already detect, oh, it is well connected to the previous 10. And then we can make a suggestion that whether or not this one is risky or more, something like that.
Cool, thank you.